Okay, so all right. So hello everyone, welcome back. So today I'm going to try to write on the board and keep the tablet upright so you can still see me. I hope it works. So let me just remind you what we did last time. So we studied model categories, which were given by 3 classes of morphisms. So you had the category C, and you had W, which were weak equivalences, cofibrations, and fibrations. So elements of W are what we want to invert. And these are auxiliary data, which is used to have a better understanding of the homotopy category, which is to say, as we saw last time, very briefly, the localization of C with respect to W. All right. This is what you started to study last semester. So what we are going to see this semester is how to use this auxiliary data to be able to work better with localization. So let me just remind you what we did briefly at the end of the last session. So we briefly defined the homotopy category, which was the localization of C with respect to W. So let me remind you of the definition. Let C be a category and W a class of morphism. So someone made the comment last time that you need to assume that the localization sends morphism of W to isomorphism. So let me write the full definition. The localization of C with respect to W is, so it's a category and the functor. So I would just say it's a functor. Lambda from C to another category, which is usually denoted C bracket W minus 1, such that, first of all, lambda sends elements of W to isomorphisms. And moreover, for any functor f from C to D that sends W to isomorphisms, there exists a commutative diagram like this, which is unique up to equivalence. So this is a notation for that. There exists a unique f bar from C bracket W minus 1 to D, such that the following diagram commutes. All right. So this is what we did last time. So are there any questions before we go on about this definition? So as you saw in the previous lecture, so Homotopy 1, there is a way to construct this localization. So the localization can be constructed as follows. So you can denote it by, so the objects of C bracket W minus 1 are the objects of C. You keep the same objects, but for the morphisms, you do something different. So the morphisms in C bracket W minus 1 between X and Y are paths with respect to W between X and Y modulo some equivalence relation where path between X and Y are sequences like this. So X, let's call it X0, goes to X1, gets a map from X2, and so on. And that Xn, which is Y. And all the maps which go in the wrong direction are assumed to be elements of W. All right. And you have the equivalence relation. Is generated by two kinds of elementary identifications. So whenever you have a map in one way and the same map in the other way, then this is identified with just X. So that is to say you collapse the thing. Or similarly, if it's first F in the wrong direction and then F in the correct direction, you can collapse it. So essentially, it means that these maps which go in the wrong direction are kind of like formal inverses of elements of W. And finally, you have an identification where whenever you have two maps in the same direction, when this is identified, so it should be, let's say, Z and this is Y, then this is identified with a composition. Right? So this is one way of constructing the localization. You can check, it's not very hard, but the obvious functor which sends an object to itself and a morphism to length 1 path is the localization of C with respect to W. Okay, so is this, I think you saw this last semester, so I think you should be all right, but are there any questions about this? No? Okay, so this construction works fine. There is a slight issue for it's the size. So this this construction, this set here is actually not a set. It's a class because there could be as many elements as there are objects in the category. So even if we assume that there is only a set of morphisms between two objects, there can be a proper class of morphisms in the path category. So it's a slight issue, but it can be fixed. It's not really a problem for us. But the real issue is that it's very hard to do computations. So for example, if I give you two morphisms in C, right? I give you some morphisms between X and Y. Are they equal in the localization? Well, this is a very hard problem. It's basically, it's related to what is called the word problem in group theory. I give you, let's say, a presentation of a group, and I ask you, are two words equal? It's not an easy question. In fact, it's a very difficult one. And related, well, it's another way of stating the same issue. how do you actually compute this this morphism set? What is it? Because this is what is above is the definition, right? But it's not easy to work with it. Like, for example, if I wanted to ask how many classes of maps, like how to actually count them, how do you count them? It's not easy at all, right? So the goal of what we are going to do today, and maybe finish Friday, depends on the time, is a way to use these auxiliary data in order to have a better understanding of this set, right? So is this okay for everyone? No questions? Okay, so I gave a few examples of localizations in the notes. Be aware that there was a mistake in example 1.4.6. You had to assume that the monoid was commutative, as we said last time. But we are now going to go into how to apply the theory of model categories to have a better understanding of its localization. So let me make just one definition. So if C, W, C, F is a model category, its homotopy category. So this is just a notation. It's called Ho of C, and by definition, it's simply the localization of C with respect to W. All right, so this is the thing that we are interested in. It only depends on W. If you have two model categories with the same W but different cofibration and fibration, we will have the same homotopy category. What is going to change is the presentation of the homotopy classes of maps that we are going to present next, right? But the homotopy category itself will be well defined up to equivalence of categories. So there is nothing that changes here. So before we start dealing with homotopies, let me just make a preliminary lemma. So we are going to define 3 subcategories of C. So you have CCF, you have CF, CC, and C are subcategories of, so you have fibrant, cofibrant, and fibrant, cofibrant objects, all right? And here in C, you have all objects, okay? So you take your category C, and you consider the subcategory formed by all fibrant objects, or the subcategory formed by all cofibrant objects, or the subcategory formed by all objects which are at the same time fibrant and cofibrant. So as a remark, these objects are sometimes called bifibrant, but this isn't really standard. I mean, I've seen this in a lot of places, but other authors do not use this terminology. Okay. So before we go on, let me prove this lemma. So these inclusions induce equivalences between localizations. So you have the homotopy category of C, which is C bracket W minus 1. Inside of this, you have a functor from the localization of CC with respect to C to W. So using the universal property of the localization, there is a functor between the two. Well, I shouldn't write that it's an inclusion because that's not obvious. Also this one goes in here, and also this one goes in here. And the lemma is that all of these functors are equivalences of categories, right? So if you want to compute the homotopy category of C, you can localize the subcategory of cofibrant objects, or the subcategory of fibrant objects, or the subcategory of bifibrant objects with respect to W. And of course, here, when I write W, I of course mean the intersection of W with morphisms between cofibrant or fibrant objects and so on. All right, so you can restrict to this smaller category. All right. So the proof is not very hard. I will only do one of the proofs. The other three are completely identical. Right, so someone apparently enabled their microphone. Okay. So let me do the case for fibrant objects. You are going to see that all the other cases are completely identical. All right. So we are going to prove that this functor is an equivalence of categories. And to do this, we are going to provide an inverse of this functor up to homotopy, or sorry, up to natural isomorphism. So this inclusion induces a functor from CF, sorry, from CF localized to C localized. Okay. So we are going to make a functor in the other direction, and to provide this functor, we are simply going to use the fibrant replacement functor. Okay, so there is before I go on, there is a question in the chat. Are CF and C model categories? No, not necessarily. Well, basically, yeah, for example, they can be not bicomplete. It's possible. For example, if you, I guess if you take the product of two cofibrant objects, it's not necessarily the case that the product is cofibrant, for example. The coproduct will be cofibrant, but not necessarily the product. There are other issues, like, well, I guess the lifting lemmas will work, but the factorization axiom maybe will be a problem, I guess. But these categories are what are called the categories of cofibrant objects or categories of fibrant objects. It's something that exists where you only have one half of the model structure, but not the other half. I will let you look it up. We are not going to talk about it, but anyway. So we have this functor. To do it in the other direction, we are going to use the fibrant replacement functor. So to produce C bracket W minus 1 to CF bracket W minus 1, we use the fibrant replacement functor, so which I denoted by R, which goes from C to CF. Okay, so by the universal property of localizations, R induces R, let's call it R bar, between the localization of C and the localization of CF. All right, this functor, if you post-compose it, oh, sorry, if you post-compose this functor with the localization of CF, you can check pretty easily that it sends elements of W to elements of W, all right? So you get this diagram. And so you have a functor in the other direction. You have C is included in CF. This obviously sends elements of W to elements of W. You have this functor R bar. And maybe for consistency, I can call this one I bar. And so now we need to produce natural isomorphisms, R bar, circle, I bar, to the identity of C bracket W minus 1. So this needs to be a natural isomorphism, and also a natural isomorphism like this. All right. So to produce this one, we use the factorization. Okay. So the factorization produced by MC5. All right. If you remember, how is this vibrant replacement functor produced? You have a canonical map from X to the terminal object. This is factored as an acyclic cofibration followed by a fibration. It is this object that you call the vibrant replacement functor. And so let's call this this acyclic cofibration Jx. Then you can check that Jx is a natural isomorphism. So it is natural because I assumed that factorization were functorial. So this thing here is natural. And it is an isomorphism in the homotopy category because it is acyclic. So it is a natural isomorphism between R bar circle I to the identity and also I bar circle R to the identity. Because basically it is, oh, and I guess it goes the other way around actually. It is a map between the identity of X and either you take X, which is vibrant. So let's say, for example, we want to check that R bar circle I bar is isomorphic to the identity. So you take a vibrant object X, you see it as a general object, and then you apply the vibrant replacement functor to it. So you get R bar circle I bar. Or the other way around, if you have a random object, you apply the vibrant replacement object, and then you forget that it is vibrant. And you get I bar circle I bar, R bar. And in both cases, Jx is a natural isomorphism between the identity and the functor. All right. So this proves that this functor here is a natural isomorphism. Okay, is this okay for everyone, this lemma? So of course, for the other three functors, you do the exact same thing. For this one, you take the cofibrant replacement functor. And for these two, you need to do a little bit more, but it's essentially still the same proof. You also take the fibrant or cofibrant replacement functor, and then you just check that if you start from a cofibrant object, so for example, if you started from a cofibrant object X, then this fibrant replacement is also cofibrant, because if you have a cofibrant object, it means that this map is a cofibration, and you compose it by this acyclic cofibration, it's still a cofibration. So the map between the cofibrant sorry, between the initial object and R of X will be a cofibration also. So you stay inside the category of cofibrant object. For example, if you want to prove that this functor is an equivalence. All right. So is this good enough for everyone? Any questions so far? No. So now we have simplified a little bit our localization. So for example, if we are in topological spaces and we have a Quillen structure, we know that we can restrict ourselves to CW complexes, for example, or generalized CW complexes. But it's still not good enough because we need, when we have these generalized CW complexes, a good description of the path categories between the two. And in general, it's very hard. So what we are going to establish now is what we know, for example, in topological spaces, is the Whitehead Theorem. When we have CW complexes, then sorry, when we have a weak equivalence, it is automatically a strong equivalence. And so we can invert it. And so, for example, if we have a path like this one, if these are all CW complexes, then whenever we have a map in the wrong direction, we can invert it and go in the correct direction. And then we have all maps in the correct direction. And so we have a direct map from X to Y. And then all that is left to do is take all maps between X and Y and mode out by the relation of homotopy, right? This is what you usually do in topological spaces, right? You take all maps and then you mode out by the homotopy relation. So we are going to prove that in a model category, this is exactly the same. We are going to start from all objects and the localization. We restrict to the good objects, the models, the cofibrant objects. And between these objects, the homotopy classes of maps are precisely that. Homotopy classes of morphisms between two objects and not paths that can be very complicated. Right? So this is the goal for, I hope, today, and if not, Friday. So any questions before we start doing that? No questions? Yeah, sorry. I ask a lot of times if there are questions because with online classes, it's very hard to just start talking and not let anyone ask questions. So anyway, so what we are going to do first is to describe better this notion of homotopy. All right. In topological spaces, in order to say that two maps are homotopic, right? We don't say something like they can be connected by, like for example, if you have two maps like this, all right? To say that they are homotopic, you could check that there exists some very complicated diagram like this. Where this composite is in the same class as F and this composite is in the same class as G, right? This would be awful. Instead, what you do is you just look at the maps F and G, and there is a notion called the homotopy, which is another map that uses some kind of cylinder. So you just take the cylinder on X, and then you ask that there exists some homotopy like this, which restricts to either F or G when you restrict to either 0 or 1, right? And this is much simpler. So this is exactly what we are going to do in an arbitrary model category. So this is a notion called homotopy. Maybe I should say homotopies, because there are two kinds of homotopy, depending on whether you look at the target or the source of your map, right? Topological spaces doesn't really matter because essentially, we always use what we are going to call left homotopies, but there are also right homotopies. And depending on what you want to do, maybe better to use one or the other, right? All right, so so in the whole thing, I'm going to fix a model category, right? I'm not going to leave it. So let A be an object, a cylinder, for A, definition, is a factorization So you have A and the coproduct of A with itself, right? This is my notation for coproduct. I'm always going to use this one. It's first cofibration into some object C, C as in cylinder. Hopefully we do not confuse this C with the C for the category. I hope it's going to be clear. Followed by a weak equivalence into A of the map from the coproduct to A itself, which is kind of like the co-diagonal. Right? So you have this map from A coproduct A into A, which is given on both factors by the identity. And you factor it as first a cofibration followed by a weak equivalence. All right? So this is a bit of an abstract definition, but let me give an example and it will be much more clear. So let's take a top with the Quillen structure and A be a cofibrant space. So for example, a CW complex. Then a cylinder can be given by, well, a cylinder, which is to say A cross 0, 1, and you project down back to A, right? And you see this coproduct as A cross the boundary of the interval, all right? So this is an example of a cylinder in the topological category. So this is if you want, I can even draw a picture. You take, for example, a circle, and you take a cross product with a segment, right? And this is what is usually called a cylinder. Another example, maybe you take CH of R with the injective structure. So already you see that it's important to know what kind of structure we talk about. So for the cylinders, which will correspond to the left part of the homotopies, basically in the injective structure, it will work better than what works for the right part of the homotopies. Okay. And you take A star, a chain complex, then a cylinder can be given by the following. Cn is simply An plus An plus An minus 1 with the following differential. D of x, y, and z is, all right, so dx plus minus 1 to the n z, dy plus minus 1 to the, oh sorry, it should be minus 1 to the n z and gz. All right, then this is a cylinder. Okay, you can embed A plus A into C star like this, and this is 0, and you project by a homotopy equivalence, or more precisely a quasi-isomorphism down to A by sending X, Y, Z to I think simply X plus Y. Yeah. All right, and you can check that this is a configuration, which the injective structure simply means an inclusion. This is obvious. And this is a quasi-isomorphism, all right? Because this differential essentially tells you that if you have some Z, then Z on the, so basically Z 0, 0, and 0, Z 0 are identified by this if Z is a cycle. All right, so the inclusion in the first or the second factor are identified by this differential. It's complementary. So this is basically the idea. Okay, so this is the notion of a cylinder. Maybe a small comment here for simplicity. I ask that this map is a cofibration. In the literature, it's not always asked. And what I have defined here is traditionally called a good cylinder, because I ask for this one to be a cofibration. It's not always asked, but it's simpler, and good cylinders always exist. Maybe I should say, maybe I can write it as a lemma. Any A admits a cylinder. Proof factor the codiagonal as a weak cofibration followed by an acyclic fibration by MC5. All right. And this is so someone asked in the chat what I was going to say. You are correct. We only ask for the second map to be a weak equivalence. We could ask for it to be an acyclic fibration. So actually, axiom MC5 produces what is called a very good cylinder. Okay, the terminology is not very inventive, but it's life. Where you ask the second map to be also a fibration, but it's not necessary for most arguments. Sometimes I will need a fibration here, and I will show you that you can always replace any random cylinder by a very good cylinder. But it's simpler to just take a weak equivalence here, because this way we have more cylinders, right? We have more options for cylinders. There will always exist one where this is a fibration, but it's not needed for our purposes, right? For example, in this injective structure, if I needed to check that this map, all right, okay, and here I made something very bad. I wrote symbol for fibration. It's not necessarily a fibration. If I needed to check that this map was a fibration, then it would be much more complicated. Here I only need to check that it's a quasi-isomorphism, which is much simpler. All right, there will exist a cylinder where this is a fibration too, but it's more difficult to describe. Here I have a simpler cylinder, and for most purposes, it's enough to have a cylinder like this. Okay. All right. So we have cylinders. Now we are going to use them to define homotopies. As I explained before, for example, in topological spaces, what is a homotopy? It's a map from the cylinder such that when you restrict here, you get the maps you had at the beginning, F and G. And so this is exactly the definition. Left homotopy between F and G that go from A to X is the data of, well, a cylinder a morphism H that goes from the cylinder to X, such that the following diagram commutes. So when you go to the cylinder, then you go to H to X, here you get F and G. All right. So in topological spaces, if you take the cylinder I gave before, it's exactly the definition of a homotopy, right? Oh, I forgot to make one notation. These two inclusions, well, not necessarily inclusion, but these two morphisms, I will call them I0 and I1, right? Just a notation. Okay, so in topological spaces, this precisely matches the definition of a homotopy, as usual. Also in chain complexes, it's a small exercise to check that if you take this cylinder, right, and you take this notion of homotopy, then you get what is usually called a homotopy between two chain maps. Okay, small exercise, I will let you check. Maybe one remark is that this is a bit misleading because in these two examples, you can always take the same kind of cylinder for all your homotopies. But in general, if you have two arbitrary morphisms in an arbitrary model categories, how to say it? It's not possible to take the same cylinder for all the homotopies, right? So a left homotopy is really the cylinder is part of the data. And if you have different morphisms, maybe they are homotopic, but through a different cylinder, okay? So you cannot necessarily take the same cylinder for all the homotopies. So if such a homotopy exists, we write F is homotopic, is left homotopic to G. And as you can guess, there will be a definition for right homotopy. Okay? So our goal is to prove that in the homotopy category, so the localization, you can check if two morphisms are equal just using left homotopies and not paths, right? Paths of maps. Okay, so any questions so far? No? Okay, so let us prove some properties of homotopies. Then I'm going to do a quick dual thing where I define right homotopies and write down some of the properties, but everything will be proved dually. Actually, you can already guess what a right homotopy is. It is a left homotopy in the dual category, in the opposite category, right? So if you want to get me trying to define it, anyway, but we are going to do it properly later. All right, so
excuse
yes?
me.
Yeah.
Je pense que vous avez fait une petite erreur. C'est plutôt un cylindre A union A dans C dans A.
Oui, bien sûr. Oui, désolé. So there was a little mistake here. This thing was an A, not X. All right. But H goes from C to X. Oh, and by the way, I have a convention which I try to follow, is that the source of a morphism will be A, B, C, and so on. And the target will be X, Y, Z, W, things like that. Okay, it is a little convention that makes things simpler sometimes. Okay. All right, so the proposition, it's statements that sound obvious. So if you think about topological spaces, all these statements will be completely trivial, but we still need to prove them in arbitrary model categories. So first of all, sorry, I'm going to mute you to avoid background noise. So if F is homotopic, is left homotopic to G, all right, then for all H from X to Y, H circle F is left homotopic to H circle G from A to Y. Right? So this sounds obvious. It's not. So in topological spaces or chain complexes, it is obvious, but not here. Well, okay, this one is not the hardest one. So if H from C to X is a homotopy, then H circle H, so between, let's say, F to G, then H circle H is a homotopy between H circle F to H circle G. So this is a map from C to Y. All right, you can check very easily that if I have a homotopy like this, and all I need to do to get a homotopy between H circle F and H circle G is simply to compose like this. All right. Okay, so this is not the hardest proposition. But what we want is the other way around. Like if we have a morphism between A and B, right, and a homotopy between maps from B to X, are they homotopic when you pre-compose with your map between A and B? And this is much harder, right? Because here, if you have, so let's do it the other way around. If you have any map from B to A, and you have a morphism like this, then you can try to pre-compose like this, but this is not necessarily, sorry, what I'm trying to say is that this is not necessarily a cylinder, right? So you have to work more in order to prove that there is a left homotopy. So let's go. So first of all, and sorry, I should have said what we are going to prove is that this actually does not always work, but it's going to work for cofibrant objects. And so we start to see that cofibrant objects play a very important role, especially for the left part. So that is to say the sources of the morphism, right? So is there a question?
The arrows are not right on the diagram. H must be from C to X.
Oh, yeah, of course. Okay, this is H, this is little h, this was F and G, and this was H circle F, H circle G. Right, sorry. Yeah. Yeah, okay, and maybe if I write everything correctly, it becomes clearer why it doesn't work if you have some B here, because maybe if you have a map from B to A and you want to pre-compose, then okay, you have a map into X like this. But the problem is that even if this is a cofibration or you do not ask the map from B to be a cofibration, problem is that you have something like this. Here you have identity, identity. But this is not of the form of a cylinder because you would need something in the middle here to be a cylinder and to go here in order to have a map from B coproduct B into X. All right. So this is why post-composition works well, but pre-composition is not so clear. All right. So in order to build this C prime here, we have to add an additional assumption that B is cofibrant. And this is what we are going to prove now, that if the source is cofibrant, then we can pre-compose our homotopies, which is something that we want about the homotopy category, right? If we have two maps and we pre-compose them, we want them to be still homotopic. Okay, so let A in C be a cofibrant object. If A coproduct A in C and to A is a cylinder, then I0 and I1 that go from A to C. So the two components of this cofibration are acyclic cofibrations. All right, so this is a little technical lemma. So first of all, and this is something that is useful a lot of the time, because A is cofibrant, then the map, the inclusion of A into its coproduct with itself is a cofibration. Why? Because you have a push-out diagram like this. By definition of the coproduct, right? So this is a cofibration because A is cofibrant, and cofibration are closed under push-outs. We saw this last time. So this one is a cofibration. So this is cofibration because cofibrations are closed under push-outs. So this is something that you can keep in mind, right? If you have a cofibrant object, then because of this commutative of this push-out diagram, the inclusion here is a cofibration. Right? This is something very general. All right. Therefore, I0, so the map I0 goes from A to C. It's given like this. You go from A into its coproduct, and then you go into C. So this is a cofibration because we have a cylinder. This is a cofibration because of what I just explained. So therefore, it is the composition of two cofibration, and it is therefore a cofibration. Okay. So this is the first statement that I0 is a cofibration from A to C. And for this one, you really need A to be cofibrant. Otherwise, it doesn't work, even if this thing here is a cofibration. Okay? You should be careful. Huh? This map here is not always a cofibration. All right, the second part of the lemma is that I0 is acyclic, right? That it is a weak equivalence. And this is true in general. You don't need A to be cofibrant for I0 to be a weak equivalence. Because you have a map like this. You go from A to A, coproduct A, then you go to C, then you go to A back. This map here is I0. This map here is the identity, okay, which is an isomorphism and is therefore a weak equivalence. We saw this last time. And now you can apply 2 out of 3. You have a triangle like this. So this is the top map in red. Okay, I will try to be consistent with colors. You have this map in green, which is a weak equivalence. And here you have I0. And so by 2 out of 3, I0 is a weak equivalence. Okay, you have two sides of the triangles which are weak equivalences. Therefore, the third side is a weak equivalence. Okay, and this is true whether A is cofibrant or not. It's true in general. All right, so why do I state the lemma like this? It's because acyclic cofibrations are nicer than just plain weak equivalences. Because, for example, we saw last time that they are closed under pushouts. And this is something that we are going to use. Because if we only knew that A0 was a weak equivalence, we could not push it out along an homomorphism and still keep a weak equivalence. We really need A to be cofibrant to have this kind of result. Okay. So any questions about all this? Is it okay for everyone? No? Okay, so I'm going to prove a proposition, then we can have a little break. All right, so if A is cofibrant, then this relation is an equivalence relation on this Hom set. So someone is asking which one is for I1. I wrote I0 in both arguments. It's the exact, you do the exact same thing. You essentially, instead of using this map, you use this map, but because this map is a cofibration, this map is a cofibration too, right? And therefore the composite is also a cofibration because instead of including into the first factor, you included the second, but it's completely the same. And also here, if you included the second factor, you still have the identity here by definition of the cylinder. So the argument for I1 is completely identical, right? Is it okay? No, okay. All right, so this is the proposition. So if A is cofibrant, then this thing here, the left homotopy relation, is an equivalence relation with the Hom set. All right. So maybe it's been 1 hour, so we can have a break now, I guess, and do the proof after the break. So before I stop the recording, if there are any questions I can answer. No? All right, so let's have a 5-minute break. All right, so let's check that this relation is an equivalence relation. So the only difficult part will be to check transitivity. Reflexivity and symmetry are easy. So reflexivity. So let's let F go from A to X and take any cylinder like this. Then you can just take kind of like a constant homotopy, right? You just take F, which is, you should think of this as you take F for any possible time component, right, is a left homotopy between F and itself. You have symmetry. So let F G be maps from A to X, and take a homotopy between F and G. But of course, you assume that, let's say, F is on the left and G is on the right. And we need to find a homotopy between G and F, okay? So you let sigma be the isomorphism that swaps both factors, right? So it takes the first A to the second A and the second A to the first A, okay? Then H circle, no, sorry, it's you take a different cylinder. So you start from A to A, you apply sigma, and then you take this map I. All right. Because this is an isomorphism, this is a cofibration. I is a cofibration, so this is a cofibration. And you go back into A. And here, if you do H, then because here you have F, G, here you have G, F, because you swap the two things. So it's the same homotopy, but the cylinder is different, right? What is considered the, let's say, t equals 0 part is what was before the t equals 1 part. And similarly, what was the t equals 1 part is now the t equals 0 part, all right? So therefore, G is left homotopic to F. Okay. And so now to conclude, we need to check transitivity. And this is what is the most difficult part. And this is where you need to use the fact that A is cofibrant, right? Because so far I haven't used it. So transitivity, assume that F is left homotopic to G and G is left homotopic to H. And hopefully we try not to confuse this H with a homotopy. So they are all mapped from A to X. So by hypothesis, you have two cylinders. The first cylinder, like this. Voilà. To A, here you have big H, okay? And another cylinder like this. And as I said, you cannot assume that they are the same cylinders. It is possible that, and anyway, it will not even be relevant that they are the same cylinder or not, but you cannot assume that they are the same. So this is what I put a C prime here, and here it's I prime. All right, so you have to, we have to define a cylinder which will serve as a way of making a homotopy between F and G. So how do you do it in, for example, topological space? Well, you have a first homotopy between A cross 0, 1 to X, and another homotopy between A cross 0, 1 to X. What you do is you say that A cross 0, 1 is A cross 1/2 union A cross 1/2 1 over A cross 1/2. All right, and this is a cylinder and this is a cylinder. And so you glue the two homotopies, and at the first part you have F, the last part you have H, And they agree on the middle because it's a homotopy between G and G. All right. Oh, yes, you are right. This part here should not have been F, it should have been H. Sorry about that. All right. So this is roughly speaking the idea. To get the new cylinder, you glue the two cylinders along the right part of the first one and the left part of the second one. You glue them and you do something like this. You have this first cylinder and this second cylinder. You glue them here and you get a new cylinder which serves as a homotopy. So maybe I draw a nicer picture. Up. So this is 0, 1/2, 1. And you get a new cylinder. So this is exactly what we are going to do, but in a categorical language. All right. So to define this new cylinder, as you can see here, it's defined as a push out. So we define it as a push out. And this is a push out along a common part A. So we start from A, we have C prime and C. And so we glue the the right hand, doesn't really matter. So actually the I1 part of C with the I0 prime part of C prime. And we define as a push out C secant, right? Which is C union A C prime, but you have to be careful that you glue the last part of C with the first part of C prime. All right? Is it clear, this push out? You have to think about this picture. So using the lemma, this is a acyclic cofibration. This is an acyclic cofibration. Acyclic cofibrations are closed under pushouts. And this is where we use the fact that A is a cofibration, because if this were just a weak equivalence, here we could not say anything because the pushout of a weak equivalence is not always a weak equivalence, even in topological spaces. So therefore, this is a weak equivalence, this is a weak equivalence. All right, you use the lemma, and you use, so the lemma that was here, right? And you use the fact that acyclic cofibrations are closed under pushouts. So this is an acyclic cofibration, and this is an acyclic cofibration. All right. So we are going to use this later. And we want to define the map to A. So we use the projection. So maybe let's give it a name. This is P prime. So you use P here, use P prime here. And by the universal property, right, this whole thing commutes because this is the identity and this is the identity. So they agree. Here you get a P secant. And so we get at the end a cylinder like this, where to go from A, coproduct A, into C secant, you use essentially I0 and I1 prime. All right. So you use this part, and you glued along this part. All right. You can check that it is a cofibration because, so this is cofibration because push out of cofibration. Yes. No, okay, I think I'm saying something wrong here. It's not necessarily a cofibration, but if it is not, you factor it. All right, sorry. You factor it as a cofibration followed by an acyclic fibration, and this would be C third, right? And so this will be the first part of your cylinder, and this will be the second part. And so the only thing left to check is that p second is acyclic, right? But to show this, you just use, for example, this triangle here. This is a weak equivalence, for which we needed the cofibrant here. This is a weak equivalence by definition of the cylinder. So therefore, oops, sorry. So this here is a weak equivalence using 2 out of 3. 2 out of 3. This is the lemma. And this is closed under push out. All right. So we finally have a cylinder. And to define the map into X, we use the universal property of push out. Here we have F and H. All right, so this is a bit of a complicated proof. There is a lot going on, but hopefully the idea is somewhat clear, right?
Excusez-moi.
Oui.
Juste, on n'avait pas dit qu'on devait refactoriser par un C triple.
Oui.
Et du coup, l'application vers X ne devrait pas partir de C triple.
Si, mais en fait, au cas où c'est pas C secondes qu'il faut prendre et c'est C triple, on prend juste ce truc-là.
Oui, d'accord.
Voilà. Oui. All right. So what I just said is that in case this map here is not a cofibration, you factor it like this, so you have cofibration. And to get the homotopy, you consider this composite here. All right. And this whole thing is FH, so like it doesn't matter if you cut here or if you cut here. All right.
Excusez-moi.
Oui.
J'ai raté pourquoi A union A dans C secondes, c'est une cofibration.
So it's not necessarily a cofibration, but if it's not, or you can do it all the time, you factor it as a cofibration followed by an acyclic fibration, and actually this is your cylinder, right?
Okay. I get that. Thank you.
Right. H triple is H second composed with this thing here, right? Yeah, I'm not sure that this map here is always a cofibration. Maybe it is, but it's not clear. But anyway, we don't need it because we can just factor this map here and still get a homotopy. All right, the important point is that this map here is acyclic. Like, this is very important. All right. So any questions about this proof? So as you can see, the ID, it will be something very frequent. The ID in the model category thing is very close to the topological ID. It's just that in order to get all the details right, you need to really use all the tools at your disposal and really use all the axioms and the properties and so on. But the idea is just this picture, right? Just you have two cylinders, you glue them, and voila. All right, so we have our equivalence relation. Now we are going to prove that we can pre-compose. So as we saw earlier, we can post-compose homotopies, all right? But we had this issue where we could not pre-compose because we did not have this C prime here. All right. Actually, I'm going to Okay, let's do it now, I guess. So if X is vibrant, so now we have a condition about the target and F circle F is homotopic to G as map from A to X. Then for all H from B to A, F circle H is homotopic to G circle H as maps from B to X. All right, so now it's a bit different. We have a condition about the target. Okay. So this is also a general feature of model categories. Very typically, the source will be asked to be cofibrant, and the target will be asked to be fibrant. Because if you remember the lifting properties, fibrations were always on the right, on the target side, and cofibrations were always on the left, on the source side. All right, so the proof, let's do it. So let's assume that we have a cylinder. This is I, this is H, X, and this is F and G. Okay, and this is A. And for good measures, let's call it P. I don't know if we are going to need it. All right, so we want basically to do what I tried to do here, which is to say to find some C prime here. And the problem is that we cannot always factor the map, so the co-diagonal here, through C. But if we have some lifting things, as we are going to see, we are going to be able to do it. So let us factor. So I have to check my notes because it starts to get a bit P. All right, so this one as, so C goes to some C prime goes to A. And because P itself is acyclic, doesn't really matter whether I ask the first or the second one to be acyclic, because by the 2 out of 3 property, this map here, P is acyclic. So if either one of these two is acyclic, then so is the third one, right? Okay. And so now we use our hypothesis that X is vibrant. We have a lift. Okay, so we have C goes by an acyclic vibration to C prime, goes to the terminal object. This is a vibration. This is H, all right? And so here you have your homotopy H prime. And now we are going to check that this produces a homotopy between F circle H and G circle H. So I heard something. Did someone try to ask a question? No? Okay. So maybe it's the building, there are some works. All right. So H prime is a homotopy between F and G. All right. We still have a diagram like this. All right. C prime, H prime, H, F, G. All right. So this thing here is still a homotopy. But what we have gained is that this thing here is an acyclic vibration. So if you remember at the beginning, someone asked, do we always assume that this thing here is a vibration? I said no, but we can always replace any homotopy by a homotopy in which the second part is an acyclic vibration. So, but only if the target is vibrant, right? So because the target is vibrant, we can have a homotopy in which the second part is a vibration, right? Using this lifting property. Okay. So if you need to remember it, if the target is vibrant, then any good homotopy can be replaced by a very good left homotopy. All right. So now we are going to use this to our advantage. We want to define a homotopy that goes from is a cylinder for B. So here we have our map from the coproduct of B with itself to the coproduct of A with itself into A. We go into C prime. We have our acyclic vibration here, but maybe I call P prime. So this is a P prime everywhere, all right? Into A. Then we have some D here and some B. So I should have said fix a cylinder for B. So B goes like this. This is H. So now we are in a good setting because on the left we have cofibration. On the right we have an acyclic vibration. So we can find a lift here. Let's call it G as in homotopy. Then I let you check that G is, oops, sorry. So you have here, it goes into C prime. It's not easy to write on this thing. So if you compose this G with the H prime, I guess, from before, then this is a cylinder as assumed. And this here is F circle H, G circle H. Because when you compose H prime with G, it becomes the same. So H prime goes from C prime to X. It becomes the same as composing it with, and you compose it with this. So it becomes the same as composing with this thing here, which is precisely this morphism and H circle H, H coproduct H. So in the end, you get this composed with this, which is precisely this. All right. So another of a bit of a technical proof, but again, I mean, it's a bit long, but there is not a lot going on. It's just this idea I gave before. You have your cylinder here, and you want to find the cylinder here from which, where you have the G here that you want to compose, all right? And so the whole setup is to be able to apply the lifting properties and get it in a way in which you can factor everything like that. All right. So any questions about this proof? So maybe they go a bit fast. What I would suggest is that, well, you try to do them on your own again, right? Without looking at the proof. Try to set things up in a way in which you can apply the lifting properties. So essentially what you want is always, you start from your cylinder here, and you want it to factor through C prime, your map from B to A, right? So you set everything up so that you have an acyclic vibration here, and you lift. Okay, this is essentially the idea. All right, so if we, I will make a summary at the end, but what we have proved is that we can pre-compose homotopy, we can post-compose homotopy. We have an equivalence relation if the source is cofibrant. The last thing we want to check is that weak equivalences are actually invertible with respect if you model by homotopy. All right, so let A be a cofibrant. So let A be cofibrant. H from X to Y, a weak equivalence. If H is a vibration, which is in this case acyclic, or if X and Y are fibrant, then H star, which goes from Hom of AX mod the relation to Hom of AY modulo relation, is a bijection, which essentially means that, well, first of all, if two maps, how to say, if two maps are homotopic after composing, then they are homotopic before. And this is expected because H is a weak equivalent, so it should not change anything. And moreover, any map like this is homotopic to a map which factors through H, which is also expected. You are expecting to be able to invert H up to homotopy. So there should exist some kind of right inverse. And so you should be able to factor any map like this through H. All right? And as you can see here, we have to combine both hypotheses. The source has to be cofibrant, and the targets have to be fibrant. Or H has to be a fibration. And as we are going to see, these two conditions here are very related. It's often the case that we have a result which is true when at the target we have something which is either an acyclic fibration or a weak equivalence between fibrant objects. This is something that is called the Bronze Lemma. We are going to just apply it in a particular case here, but it's something very general. So let's go about the proof, except if someone has some question before we begin. No? Is it okay? So really this proposition here is very typical, right? The source is cofibrant. The target is either a fibration or a weak equivalence between. All right, should be more precise. What is true is that what's similar are acyclic fibrations or weak equivalences between fibrant objects. This is the content of Bronze Lemma. And as I said here, we are going to see it in a particular case. So let's go about the proof. We are going to do both cases, and this part will be a consequence of this part, right? So let us first assume that H is an acyclic fibration. All right. So H star is surjective. This is by MC4, right? Why is by MC4? Well, you have this diagram like this. A is cofibrant. H is an acyclic fibration. And so there exists, as I said before, right inverse of H. And now, because H is a vibration, this is not just up to homotopy, this is an actual right inverse, right? There exists some right inverse that I'm going to call, I don't know, rho, I think, right inverse. Okay, and so for any G between A and Y, there exists an actual, okay, G, maybe rho is not good, G bar from A to X, which is mapped to G under composition with H, right? And this is on the nose, right? So on the nose is an expression that is used to say it's actually an equality. It's not an equality up to homotopy, right? So it's even a surjection before taking the quotient, okay? Of course, in the case where the targets are fibrant, then this will only be a surjection after taking the quotient. So now let's prove that H star is injective. So we have to assume that are such that H circle F, sorry, no, H circle F is left homotopic to H circle G, right? And we need to prove that F and G are left homotopic. So how do we do that? Well, of course, we use the fact that H is an acyclic vibration. Okay, so we have some cylinder. So there exists a cylinder for A such that, and the homotopy like this, such that here we have H circle F, H circle G, right? And we want essentially to be able to factor this homotopy through X. This is basically the goal, and to be able to factor it like this. All right, this is what we want to do. So as usual, when we want to factor something, we use lifting properties. So I prepared, of course, what is the lifting property we want to use? Well, we have our acyclic vibration here. We have our co-vibration here. Well, we can lift. Exists some K here, and here this is H. And K is a homotopy between F and G, right? So as you can see, the proof is not very difficult in this case. When you have actually an acyclic vibration here, you can directly use lifting properties on the nose to find actual lifts and actual maps which make diagrams actually commute and not just commute to homotopy. Okay? And to find these maps, you have to think about what you want to do. And here, it's simply to find some factorization of the homotopy here. And so you just need to set things up in a way in which you are able to use the lifting properties. All right, so is it okay for everyone, this proof? All right. Ah, no, there is a question. Ah, okay. All right, so now what we are going to do, and we are going to formalize this in a later, at a later time, but is to prove that basically is the following. We have this functor from C of A mod mod left homotopy. We have this functor. What we have just proved is that this functor sends acyclic vibrations to bijections, right? It sends acyclic vibrations to bijection. There is a very general lemma which states that if this is the case, then it sends any weak equivalence between vibrant objects to bijections. So we are going to see it now in a particular case, and later on, when we have a need of it, we are going to make it more general. But right now, we are just going to see it in a particular case. All right, so now, assume that X, Y are vibrant. So we will have a kind of a complicated diagram. All right, so let us factor the identity of X and H seen as a map from X to X cross Y as an acyclic cofibration followed by a vibration. All right, so honestly, this proof, well, once you understand it, it's not really magic, but to be able to guess it, right? I don't know. Kenneth Brown did it, and now everyone knows how to do it, but right, it's not easy. All right, so we have this factorization of the identity and H, all right? And using the lemma from before, both projections to X and Y are vibrations, right? Because you have this pullback square, X is vibrant, vibrations are closed under pullbacks. So this is a vibration, and similarly, this is a vibration, all right? So what I want to say is that these two red maps are vibrations, all right? And so now let us make the big diagram, okay? All right, so prepare yourself. You have this acyclic cofibration followed by the projection or the vibration or whatever. You have the map to Y, the map to X. We just saw that they are vibrations. We have our H, which is a weak equivalence. And here we have the identity of Y, which is an isomorphism. So in particular, it is a weak equivalence. All right. So what we want to do is that we want to apply the proposition to acyclic vibrations. And we are going to do it 3 times and deduce from these 3 applications of the proposition that H induces a bijection between hom of the things. Because all these maps, what do they induce? They induce maps like this, hom of A to X mod weak equivalence, hom of A to W mod weak equivalence, hom of A X cross Y mod weak equivalence, All right, I exchanged X and Y, sorry. And this is, of course, the identity of X. So this is Y. All right, and our goal is to prove that this blue map is a bijection. All right, this is what we want to do. And to do this, we are going to apply the lemma several times. So we are going to apply it the first time to this map, right? So the map from W to Y is an acyclic vibration, all right? Why is it a vibration? It's the composite of two vibrations. Why is it acyclic? You have a triangle here, and two sides are weak equivalences. Therefore, the third one is a weak equivalent. Therefore, this map is a bijection using what we just saw. Post-composition by an acyclic vibration is a bijection. The second map to which we are going to apply the result is a green map. So similarly, W2X is an acyclic vibration. And therefore, this map is a bijection. All right? And finally, and I highlight, we don't apply the lemma for this one, but here we have, what do we have? We have the identity. And the identity is an iso. Well, okay, you can think of it as an acyclic vibration, actually, if you want. But anyway, post-composition by an isomorphism is an isomorphism. Actually, this thing here is, in fact, the identity, which is a bijection. All right? And so now we have a proof. Because using the green and let me find a new color. So using the green and the pink bijection, this map is a bijection because bijection, bijection, bijection. And combining this with the red map, the blue map will be a bijection. Okay. I did something stupid here. All right. All right, so here you have a triangle, two bijections. So the third is a bijection. And here you have a composition of two bijections. So the third is a bijection. All right. So this is a clever argument to prove that if you have something which sends which sends acyclic vibrations to bijections, then it sends vibrations between vibrant objects. Oh, sorry, weak equivalences between vibrant objects to bijections, right?
Excuse me.
Yeah.
I've understood the reasoning, but I don't get the idea. Where, how do we think of this generalization?
I don't know, honestly. As I said, it's called the Bronze Lemma. So Kenneth Brown found it sometime. I don't remember when, actually. I gave a reference in my notes. And since then, people have been using it. So he found it in 73. Right. How did he find it? I don't know. Personally, I don't think I would have thought of it. I don't know. I guess playing with commutative diagrams long enough, you end up thinking about it. But I couldn't say what the intuition behind it is. It's really a technical lemma. Yeah, I don't have a good answer for that question, sorry.
Dommage. Merci quand même.
Ouais, voilà. Okay, so just as a summary of all we've done so far, we have a notion of left homotopies on Hom of AX. So post composition. So H star is compatible all the time. Pre-composition is compatible if X is vibrant. It's an equivalence relation if A is cofibrant. And H star is a bijection if A is cofibrant and target is vibrant. And H is a weak equivalence, of course. All right. And to do this, we use cylinders. So very quickly now, in the last 10 minutes, I will just say briefly how it works for the dual thing. All right. Because so far we have only dealt with, in some sense, the left part, the source. We still have some assumptions about the target, but the homotopy is really dealing with the source of the morphism. We have a completely dual thing, which is right homotopies. So let me just present it briefly. So next part, right homotopies. All right, so I will be quick because, and I will not give any proofs because everything is dual. So let X be some element of C. Path object for X is a factorization. So X goes by equivalence to some P as in path, of course, and then a fibration to X cross X. All right, so if you think about what a cylinder is, this is completely dual of the map given by the identity on both factors. All right, and these two projections, we can call them pi 0 and pi 1. So as an example, in top, with the Quillen structure, and X is a CW complex, or maybe a cofibrant it works, then you can take P is X to the power 0, 1 with compact open topology. Right, and P0 of F is F of 0, P1 of F is F of 1. Sorry, I should have said this notation means the set of all maps from the interval to X. Also in CH of R with projective structure, you can take, I guess, let's say it's CH of R, and A star is in CH of R. Then you can take a path object by Pn is An plus An plus N plus 1, and D of A, B, C is dA, dB, dC plus B minus C and minus A, sorry, maybe with some sign somewhere. And the the idea is the same. You can think of this as a hom of chains on the interval to A star, reduced chains. Whereas before it was the tensor product of A with the chains, right? All right. And so as before, you cannot always take the same path objects for all your homotopies, but in nice cases, you can actually. For example, in top homotopies between between CW complexes, you can always take this path object, right? All right, so let f g from A to X be two morphisms. A right homotopy between f and g is a path object, so which is something like x goes into P and then goes back into X cross X by projections, and a morphism still denoted H, because why not, from A to P such that the following commutes. So A goes to P. Oh, maybe I can do it in a way which is similar to what I did. Right. Here you have A, you have your homotopy, and here you have F and G. All right. So your homotopy, if you project it on the first factor, you have F, and if you project it on the second factor, you have G. In this case, so if this exists, right? We write F is right homotopic to G. Okay, completely dual picture. In topological spaces between CW complexes, for example, this turns out to be equivalent. And we are going to see that it's a general feature. If your spaces are nice enough, and this is equivalent to being left homotopic. But in general, it is not. Okay, I'm not going to write all the propositions, but the summary is the same. So post composition, sorry, pre-composition is compatible, right? If you have a homotopy and you have a map from B to A, it suffices to pre-compose the homotopy to get a homotopy between the pre-composition. Post-composition is compatible if X is fibrant. All right. Okay. If A is cofibrant, and X, Y are, no, sorry. If A, B are cofibrant and X is fibrant, then H upper star is a bijection. And finally, if X is fibrant, then this is an equivalence relation. Right? Okay, so I guess it's almost time to stop. But essentially, you just take the previous section, right? And you do everything in the opposite category, and you get all the results about the right homotopies. Okay? And the proofs are really dual. You take all the errors, you put them the other way around, you reverse cofibrations and fibrations, and you get the results. Okay. All right, so we have defined our homotopies now. And if you remember the goal from the beginning, the goal is to be able to compute, where was it? To compute this thing here. And the end result is that if our objects are nice enough, we can compute them as a set of maps between our two objects, modulo these two relations. So the goal for next time is to prove that, first of all, if the objects are nice enough, these two relations are equivalent. And then to prove that the homotopy category can be described using these two relations. All right? So are there any questions before we stop for today? No questions? All right, so if there are no questions, I will stop the recording.